This is a recording of Chapter 15, Atmosphere Components and Pollution. First, we'll go over the components of the atmosphere. So there are four main layers. You have the troposphere, the stratosphere, mesosphere, and thermosphere. This black line here is a graph of atmospheric pressure. The red line is a graph of temperature in degrees Celsius. Most of the air molecules in the atmosphere are in the lower section. As you can see, there's higher air pressure down here. The troposphere is the layer that's the closest to the Earth's surface. Atmospheric pressure is in millibars. The scale is up here. So as you can see, most of the air pressure is down near the Earth's surface. The air that you breathe is mostly composed of nitrogen at 78% and oxygen at 21%. And the rest of what air is made of includes argon, carbon dioxide, and small amounts of water vapor, dust, and soot particles. And then there are some other gases like methane, ozone, and nitrous oxide. And again, the troposphere is the layer of the atmosphere closest to the Earth's surface. So most of the air molecules are in the troposphere. And the stratosphere is the second layer. And you have this ozone layer, which we will talk about. Ozone, which is oxygen, there are three oxygens, is concentrated in a portion of the stratosphere called the ozone layer, and that is 11 to 16 miles above sea level. And this is stratospheric ozone, and it is produced when some of the oxygen in the atmosphere interacts with ultraviolet radiation emitted by the sun. And the ozone layer prevents about 95% of the sun's harmful UV radiation from reaching the Earth's surface. And now we will talk about air pollution. Air pollution is when there are certain chemicals in the air in concentrations high enough to harm organisms, ecosystems, or to alter the climate. We will go over outdoor air pollution, and then we will discuss indoor air pollution. So outdoor air pollution has natural and human sources. Natural sources include dust blown by wind, pollutants from wildfires and volcanic eruptions, and most human inputs of outdoor air pollutants come from industrialized and urban areas where people, cars, and factories are concentrated. There are two categories of outdoor air pollution sources. We have stationary sources. That is a source of pollution that remains in the same spot. For example, a coal burning power plant. And a mobile source, which is a source of pollution that moves around. For example, motor vehicles. And then we have a different way of classifying outdoor air pollutants into two categories: primary pollutants and secondary pollutants. Primary pollutants are chemicals emitted directly into the air from sources, and secondary pollutants may form when some primary pollutants react with one another and with other natural components of air, resulting in the formation of new chemicals. So this diagram shows various pollutants. We have a motor vehicle spewing out some air pollution. You have this plant here. Either this could be an industrial plant or a power plant, and it is emitting some air pollution. And then you have some natural sources. Here is a volcanic eruption emitting pollutants into the atmosphere. And then here you have a representation of secondary pollutants, which are being formed related to chemical reactions. This is a list of major outdoor air pollutants. We have carbon oxides, such as carbon monoxide and carbon dioxide, nitrogen oxides and nitric acid. Then we also have nitrous oxide, sulfur dioxide and sulfuric acid, particulates, ozone, VOCs, and smog. And there's industrial smog and photochemical smog. And then we will go into the details of all of these. Carbon oxides, such as carbon monoxide. Carbon monoxide specifically is a toxic gas that forms during incomplete combustion of carbon-containing materials. And the major sources include motor vehicle exhaust, wood burning, including fireplaces, forest fires, and wildfires in grasslands, tobacco smoke, and smokestacks from power plants or industrial plants. If breathed in, carbon monoxide can combine with hemoglobin in red blood cells and reduce the ability of that blood to transport oxygen. Long-term exposure, even if it's low levels, can actually trigger heart attacks and aggravate lung diseases like asthma and emphysema. At high levels, carbon monoxide can actually cause death. Less severe would be headaches, nausea, and drowsiness. So some carbon monoxide safety tips include never using a charcoal grill inside the home. Never leave a gas burning electricity generator inside a garage. And never leave a car running in a garage with the garage door closed. These can all lead to carbon monoxide poisoning. Also, if you sit in a car that has the tailpipe covered by snow, that can cause a carbon monoxide buildup in the car. So you're always going to want to clear the path to the tailpipe before warming up the car and shoveling out your car from snow. The first thing you're going to want to do is clear the area behind the tailpipe. Homes should contain carbon monoxide detectors in order to detect and alert inhabitants if there are high levels of the gas building up in the home. This can be related to a furnace or a gas stove, things like that. And then carbon dioxide. 7% of the carbon dioxide in the atmosphere comes from human activities, primarily the burning of fossil fuels and the clearing of carbon dioxide absorbing forests and grasslands. This is contributing to atmospheric warming and global climate change. Next is nitrogen oxides and nitric acid. Nitrogen oxides and nitric acid. Nitric oxide is abbreviated as NO, and it forms when nitrogen and oxygen in the air react in car engines and coal burning power and industrial plants. It could also form naturally, for example, when lightning hits the soil and when certain bacteria in soil produce nitric oxide. In the air, nitric oxide reacts with oxygen to form nitrogen dioxide, which is a reddish brown gas. Collectively, nitric oxide and nitrogen dioxide are called nitrogen oxides, or NOx, the NOx gases. Photochemical smog. Nitrogen dioxide plays a role in the formation of photochemical smog, a mixture of chemicals related to gases that are produced during heavy traffic conditions that react with sunlight. So cars and trucks, they're releasing gases, and during heavy traffic, you have a lot of these gases emitted, and then they react with sunlight, and you have photochemical smog form. Nitrogen oxides can irritate the eyes, nose, and throat, aggravate asthma, affect plant growth, and reduce visibility. Nitrous oxide, N2O, is a greenhouse gas that is emitted from fertilizers and animal wastes and is produced by burning fossil fuels. Then we have the sulfur-based outdoor air pollutants like sulfur dioxide and sulfuric acid. Sulfur dioxide is SO2. About 1/3 of sulfur dioxide in the atmosphere comes from natural sources, for example, volcanoes. Human sources of sulfur dioxide include burning of coal and oil refining. So coal can naturally contain sulfur. It has to do with how coal forms. In the atmosphere, sulfur dioxide can be converted to aerosols, which are microscopic suspended droplets of sulfuric acid. And then those droplets can fall to the ground as acid rain or acid deposition. And here is a diagram that shows different aspects of acid deposition, showing you have sulfur dioxide gas and particles being deposited. Here you have acid fog, acid rain, different things like that. So you could read through the different components of the diagram. Then we have particulates. Particulates are abbreviated as PM for particulate matter. And these are suspended particles in the air. So they're solid particles and liquid droplets that remain suspended in the air for long periods of time. And they're classified by their diameter. So PM10 is your fine particulate matter, and ultrafine is PM2.5, and those are measured in micrometers. 38% of particulates come from human sources, for example, coal burning power and industrial plants, motor vehicles, road construction, and tobacco smoke. 62% is from natural sources like wildfires, dust, and the sea salt. Particulates can irritate the nose and throat, damage the lungs, and aggravate asthma. And toxic particulates like lead and cadmium can cause significant health issues. Here's an example of a natural source of particulates. This is the Sahara Desert, and you have wind-blown dust coming off of the Sahara. And this is a dust cloud over the water, over the Atlantic. And there's more information at these two links that you can look at if you're interested. Then we have volatile organic compounds, or VOCs. Organic gaseous compounds in the atmosphere or liquids that can evaporate quickly into the atmosphere are called volatile organic compounds. For example, methane and hydrocarbons. Those are gases that are VOCs. And examples of liquid VOCs include benzene, dry cleaning fluids, and components of gasoline. So some sources of methane, we have natural sources like wetlands and human activities like rice paddies, landfills, oil and natural gas wells, livestock, mainly the livestock animals belching and releasing gas. A lot of that's going to be methane. And reservoirs behind dams, where you have organic matter built up from being carried in the river, getting trapped behind the reservoir, and then it starts to release methane. Now, methane is 25 times more effective as a greenhouse gas compared to carbon dioxide. So methane is a very strong greenhouse gas. The reason why we talk more about carbon dioxide related to greenhouse gases and global warming is because there is a lot more carbon dioxide in the atmosphere than methane. But methane is a lot stronger of greenhouse gas. And then we have ozone. Now, this is not referring to the ozone layer. It is referring to ozone that is present in the lower atmosphere, the troposphere. So when ozone is present in the troposphere, it is considered to be a pollutant. When ozone is present in the ozone layer, then it is helpful to us because it helps block UV radiation from hitting the Earth's surface and affecting plants and animals and all different organisms. So ozone is a major component of photochemical smog when it is in the troposphere or the lower atmosphere. Ozone in the troposphere can be harmful. It could cause coughing and breathing problems and aggravate lung and heart conditions. It can reduce the body's resistance to colds and pneumonia and irritate the eyes, nose, and throat. So over the summer in New York and New Jersey, right, in the Northeast, we have things like ozone alerts or air quality alerts. And those are usually hazy, hot, and humid days. And sometimes people complain that their eyes are burning, their nose is burning, their throat hurts. And that is related to the ozone pollution many times. Now, this ozone can also damage plants, rubber, fabrics, and paints. So this is a natural rubber tubing from a tire, and it has cracked due to ozone exposure. Now, if you use an ionizer, which is a setting on some air purifiers, it can actually create ozone. And for people who have lung issues, such as asthma, that can be an irritant. Also, photocopy machines produce ozone, which again could be an irritant for some people who are more sensitive, like people with asthma. I mean, it's an irritant for everybody, but some people are more sensitive, so they notice it more. Also, thunderstorms can result in the formation of ozone. It's related to the electricity of the storm. And sometimes people say that a thunderstorm has a particular smell, and that smell sometimes is actually the ozone related to the thunderstorm. Then we have smog. So there are two different categories of smog. We have industrial smog. That is a mix of sulfur dioxide, sulfuric acid, and particulates. And that is a problem in places like China, India, Ukraine, Czech Republic, Bulgaria, and Poland. Let's just add an Oxford comma right there. Okay. And photochemical smog is, again, a mixture of primary and secondary pollutants, which are chemicals that are formed in the sunlight. You have a chemical reaction that is activated by the sunlight. So you have a mix of primary pollutants and secondary pollutants. And that is a major problem in Los Angeles, Salt Lake City, Sydney, Sao Paulo, Bangkok, and Mexico City. So we will go over a little bit more about industrial smog. So because burning coal helps produce industrial smog, about 60 years ago, cities like London, Chicago, Pittsburgh, they all burned large amounts of coal in power plants and factories and for heating homes. So people in these cities, especially during the winter, were exposed to industrial smog in outdoor air, and that consisted of sulfur dioxide, suspended droplets of sulfuric acid, and a variety of suspended solid particles like soot. And then people were breathing that in. And people who were burning coal inside their homes were also exposed to dangerous levels of indoor air pollutants. This is a photo of some industrial smog related to an iron and steel factory in the Czech Republic. Today, urban industrial smog is rarely a problem in most developed countries, and that is related to pollution controls that are in place. In industrialized urban areas of China, India, Ukraine, and some Eastern European countries, large quantities of coal are still burned in people's homes, power plants, and factories with inadequate pollution controls. Because of its heavy reliance on coal without adequate pollution controls, China has some of the world's highest levels of industrial smog and 16 of the world's 20 most polluted cities. And then we have the photochemical smog. Again, that is related to secondary pollutants forming as a result of sunlight and the mixing of some primary chemicals that are emitted into the atmosphere from cars, so car exhaust. So sunlight plus car exhaust gives us photochemical smog. And it's the UV radiation from the sun that causes the photochemical reaction. So the formation of photochemical smog begins when exhaust from the morning commute from all the traffic releases large amounts of NO and VOCs into the air over a city. And then the NO is converted to reddish-brown nitrogen dioxide, which leads to the name brown air smog. So you'll see sometimes a pinkish hue in the air just over a city. If you look at a city in the distance on the horizon line, sometimes you'll see a pink hue just around where the buildings are. It doesn't go too much higher up into the air. It's kind of low to the ground, just around skyscrapers, maybe a little bit over them. But that pinkish hue that you see is the reddish brown nitrogen dioxide. And this diagram shows you, here you have the vehicles, you have the nitrogen oxides and VOCs released by the car exhaust, the interaction with the sunlight, the UV radiation, and then the formation of the brown photochemical smog. You also have ground ozone related to this. So when you have photochemical smog, you do have the ozone pollution as well, which irritates the eyes, the lungs, the nose, the throat. So when exposed to UV rays from the sun, some of the nitrogen dioxide reacts with the VOCs and forms mostly ozone, but some other pollution as well. The smog usually builds up to peak levels by late morning and irritates people's respiratory tracts, their eyes, etc. Now, some of these pollutants in the smog can actually damage the lung tissue. All modern cities have some photochemical smog, but it is much more common in cities that have sunny, warm, and dry climates and a great number of motor vehicles. Sunny, warm, and dry with a lot of cars, and that is going to be Los Angeles as an example. So here is a photo of LA with the smog in the air. And again, I mentioned ozone alerts earlier, and sometimes they're called air quality alerts, but usually these are more of a problem in the summer and in urban and suburban regions. And you get notifications through weather reports, or you see electronic signs on highways. And they show citizens that there is a higher level of ozone pollution that day. Sometimes the signs will say air quality alert, use mass transit. So ozone pollution, again, can exacerbate asthma and other breathing problems, but it also may have an effect on people who have cardiovascular disease. On days with high ozone pollution, people may find that they feel irritated in their eyes and their throats, even if they don't usually have allergies or they don't usually have asthma. Typically, these are the days where people who are more sensitive are going to want to stay inside with air conditioning. Here is an example of a sign on a highway. Air quality alert for today, please reduce driving. And you have access to different apps and websites that will show you the air quality. So this map is taken from airnow.gov. So there is a scale. It says good, moderate, and this orange says USG, which is unhealthy for sensitive groups. And then you have unhealthy. very unhealthy and hazardous. So this was from January 6, 2015. And you see the yellow in here. I put in the zip code for William Patterson University. So it shows you in the surrounding area, the air quality was moderate. And then over here, it says air quality index, AQI, was good. Then it tells you particulates or particles. PM 2.5 is good. Ozone is good. And this here was the forecast. And then here's information that for some reason does not match, even though it was the same day. So it says January 6th, good air quality is forecast across the Garden State with cold temperatures and scattered snow showers. And the number is 40, but on this map here, it was coming up as moderate. So I'm not sure exactly why it didn't match, but that particular day, the forecast over here did not match the forecast over here. But there is this scale as well. This is April 27, 2020, also for Wayne, New Jersey. And it shows AQI was 37. That's air quality index. 37 is in the good range. So that day was good. It was good here. Okay. So you can go to the website airnow.gov and you could type in a zip code and you can see what the air quality is. So here we are on the airnow.gov website, and I typed in Wayne, New Jersey. So this is November 7th, 2022, and we are good. The air quality index is 29. And then if you kind of hover over here, it kind of gives you some more information. Good, good. Okay, let's click on more. And let's get rid of this. Okay, so today's 35, tomorrow's good. And then it says also what the primary pollutant is. So the primary pollutant is particulate matter, 2.5 micrometers. Other pollutants are ozone, and that's also 35. And then you can explore some other things on this website. You can click on the map. And you do see there are some areas that are moderate. Moderate was yellow. And then you have the unhealthy values over here in California. So make sure that you go back to this website in the summer, and you might see that it's in the yellow or sometimes even in the orange section. So now we're going to move on to indoor air pollution. In developed countries, indoor air pollution is mostly related to chemicals used in building materials and products. The EPA had studies reveal some alarming facts about indoor air pollution. Levels of 11 common pollutants generally are 2 to 5 times higher inside US homes and commercial buildings than they are outdoors. Pollution levels inside cars in traffic clogged urban areas can be up to 18 times higher than outside levels. And the health risks from exposure to such chemicals are magnified because most people in developed urban areas spend 70 to 98% of their time indoors or inside vehicles. So indoor air pollution can be a serious problem. The foremost dangerous indoor air pollutants in developed countries include the following. So that is tobacco smoke, formaldehyde emitted from many building materials and various household products, radioactive radon gas, which can seep into and collect in houses from underground rocks and soil that have uranium, which is a natural material, and long-term exposure to radon gas can lead to lung cancer. Actually, exposure to radon gas is the leading cause of lung cancer in people who are non-smokers. And then the fourth is very small ultrafine particles of various substances in emissions from motor vehicles, coal burning facilities, wood burning, and forest and grass fires. This diagram has a whole lot of different examples of indoor air pollutants found in most modern homes. These are going to be in developed nations. Okay, so you could read through this. And then I added over here also burning of candles. When you burn, let's say, scented candles, for an example. So I have a link here for more information about that. So I went to open that link just now to show you, and it's no longer a usable link, so I deleted that. But we will still keep that there, burning candles. Air pollution is actually a really big killer. Prolonged or acute exposure to air pollution can overload and break down the body's natural defenses to air pollution. Fine and ultrafine particulates can get lodged in the lungs, contributing to lung cancer, asthma, heart attacks, and stroke. Years of inhaling smoke-polluted air can lead to other lung ailments such as chronic bronchitis and emphysema. I just want to go back and mention indoor air pollution in less developed countries. So the indoor burning of wood, charcoal, dung, crop residues, coal, and other cooking and heating fuels, generally they use open fires or unvented or poorly vented stoves. So these practices expose people to dangerous levels of particulate air pollution. So these are examples of the indoor air pollution problems in less developed countries. Okay, so mostly it's due to fuels being burned inside. So the other day online, I saw this article. It kind of just popped up. It's brand new. It's from October 2022. And it's about cooking fuel related to birth weight in low-income countries or lower-income countries. So here they're talking about the women's exposure to air pollution from cooking with wood or other biomass fuels while they're pregnant, having an impact on birth weight. So then apparently they found that when you reduce the exposure to this air pollution from fuels in the house while pregnant, that it does not have an impact on the birth weight. It does not improve the birth weight. Okay, so that was pretty interesting. And I will add this link into the PowerPoint notes in case you want to read more about it. So here they're talking about observations that linked household air pollution during pregnancy to lower birth rate for some 3 billion people who cook on open fires or traditional stoves using wood, dung, charcoal, or agricultural wastes. Okay, so they're saying that intervention in this did not affect the birth rates, but I'm sure it had some sort of effect if you have healthier ways of cooking and less exposure to air pollution indoors. There's going to be other benefits to your health. So it's a good thing to change anyway. Okay, so you could read the article on your own. So back to this slide. At least 7 million people worldwide die prematurely every year from the effects of air pollution. That is a very large number. And more than a third of these deaths occur in China and India. So talking about Asia with China and India, we have here a different website. It's Air Quality Index CN, so it's aqicn.org. And it's the same scale, the air quality index scale: good, moderate, unhealthy, unhealthy, very unhealthy, hazardous. And you could see areas like here, it says 453. So that's very high. And if we look back to the numbers we had in Wayne, we had, let's say 40 was our air quality index. So the scale, right? Because 100, 150, right? So if we're talking about in the 400s, that's pretty hazardous. And you can go to this website, and then also there's a section where you can type in your own zip code and it'll go there. So really you could look at anywhere in the world, but not every single place in the world has a monitor for air quality. So these are all the locations that have monitor systems. And when you click on one of the numbers, it gives you more information. Particulate matter 2.5, particulate matter 10, ozone, nitrogen dioxide, sulfur dioxide, and carbon monoxide. And when you go to the website, it has numbers there next, like as a y-axis, there were numbers, and it tells you the numbers and it tells you the air quality index. So that's a little bit of an update from when I got this screenshot. So now it has numbers, and it tells you the minimum and the maximum, and it says it's in air quality index. So that's where the numbers, these are all numbers on the air quality index scale. Okay, so that's what these are as well. Here's a closer look at air pollution in India. In 2019, the air pollution in Delhi was at unbearable levels, and they actually closed schools and they halted construction, and they had these advisories for these city residents to avoid outdoor physical activities, and that they should wear masks. and avoid polluted areas, keep their doors and windows closed. So they had a significant air pollution problem. And that is just about the same time of year, right? November 4th, 2019. So what caused the pollution? A major factor is that farmers in neighboring states burn crop stubble to clear their fields. So after you harvest crops, you're going to have just the leftover crop material. So people are burning it to clear the fields. So that is a major factor. Also, exhaust from vehicles, construction and industrial emissions contributed to the smog as well. I'm looking at the United States. This diagram shows premature deaths in the US from air pollution. And these numbers are deaths per 100,000 adults per year. So you can see in the purple, it is 30 deaths or more for every 100,000 adults every year. Mostly this is from very small, fine, and ultrafine particles emitted from coal burning power plants. Now, much of the electricity in the United States is generated by coal burning power plants. There could be up to 200,000 deaths per year. Millions more suffer from asthma attacks and other respiratory disorders in the United States. Laws and regulations can help reduce outdoor air pollution. Congress passed the Clean Air Acts in 1970, 1977, and 1990. The federal government established air pollution regulations for key pollutants. Air pollution in Manhattan used to be a lot worse before the EPA was formed and started regulations on air quality. This photo was taken in 1973, and there's a significant amount of smog. Now we will talk about greenhouse gases and the greenhouse effect. The greenhouse effect is a natural process that occurs when sunlight hits the Earth's surface, heats the Earth, and then the Earth re-radiates that heat in the form of infrared radiation back into the atmosphere. There are 4 main greenhouse gases in the atmosphere, and those gases absorb the infrared heat, and that warms the lower atmosphere and keeps the Earth warm enough for life to exist. And those 4 main greenhouse gases include water vapor, carbon dioxide, methane, and nitrous oxide. And that is a natural process. And here is just another slide with a diagram showing you a greenhouse with a similar concept. So you have the sun's rays go through the glass into the greenhouse. They heat up everything in the greenhouse, and that heat is re-radiated. Some of it is able to go out through the glass, but a lot of the heat gets trapped and is unable to pass through the glass. So the air inside of the greenhouse gets warmer and warmer. The same process warms up a car that is sitting in the sun. So if you leave a car outside in the sun, it'll heat up, and it gets pretty hot inside a car. So again, the greenhouse effect on Earth allows for the Earth to be warm enough to be habitable. Without the greenhouse effect, the Earth would be a lot colder. Now, the greenhouse effect in modern times is enhanced by the increases in greenhouse gases like carbon dioxide, methane, and water vapor that are being emitted into the atmosphere through man-made processes or anthropogenic causes. Since the beginning of the Industrial Revolution in the mid-1700s, human actions, mainly the burning of fossil fuels, have led to significant increases in the levels of greenhouse gases in the lower atmosphere. Carbon dioxide rose dramatically during that time, along with the average temperature of the atmosphere. This graph here shows you data collected at the Mauna Loa Observatory in Hawaii. And it shows the monthly mean carbon dioxide that was measured at the observatory. Now, collection of this data started in 1958. And we could see a clear signature trend of increasing carbon dioxide with the increasing of time, or 1960 or 1958. And it continues increasing as time goes on. So there was a direct relationship between time and increasing atmospheric carbon dioxide. Now, keep in mind that correlation does not mean causation. So this doesn't mean that the change in time is what is causing the carbon dioxide. This is just showing you what the trend is over time. So this is mostly related to the burning of fossil fuels. And now we will talk about climate change. So for the past 1,000 years, the average temperature of the atmosphere has remained fairly stable. But it began rising during the 19th and 20th centuries when people began clearing more forests and burning more fossil fuels. And this temperature data, the earlier temperature data before we had people taking records, the data is retrieved from ice cores. So you can get ice, you drill down into the ice, the glacial ice in Antarctica, for example, and then you can get different information from the air bubbles that are trapped within the ice. The ancient air gives you information about the temperature and various other things, various other information, including carbon dioxide levels from ancient times. Most of the recent overall rapid rise in global average atmospheric temperatures has occurred since 1978. So here is a graph. It shows temperature change from 1,000 years to, here's a little bit over the year 2000. And it shows you all of a sudden right here, a drastic increase in temperature. And this is average surface temperature from 1880. And you can see right around 1978, that's when you start having this drastic increase. That is a different slope of change than what you had before. So if you look here, it's kind of it goes up and down, but if you even it out, it's kind of a flat line. Here it goes up a little bit and then goes down kind of, and then right around here, it starts to jump keeps increasing from there. Data from the National Oceanic and Atmospheric Administration, NOAA, show that the atmospheric concentrations of carbon dioxide oscillated between 180 and 280 parts per million for approximately 400,000 years. So we had very steady between 180 and 280. That was the carbon dioxide. And it just went up and down between those two numbers for 400,000 years. Since the start of the Industrial Revolution in the mid-1700s, deforestation, burning of fossil fuels, and agriculture resulted in increased CO2. And then that rose from a level of 285 parts per million in the year 1850 to 390 parts per million in the year 2010. By the year 2016, levels reached 404, and current levels are 415.95 parts per million. Major climate models indicate that there's a need to prevent carbon dioxide from exceeding 450 parts per million. And this is a threshold that these climate models are estimating, and it's considered to be a point of irreversible tipping. So it's called an irreversible tipping point, which means once we pass that number, there's no turning back. And it's expected that it could set into motion large-scale climate changes that could last hundreds to thousands of years. The Intergovernmental Panel on Climate Change, or IPCC, was established in 1988 to document past climate changes and to project future changes. In 2007, the IPCC report that was based on 29,000 sets of data found that the Earth's lower atmosphere has warmed, especially since 1980, and that this was mostly due to increased levels of CO2 and other greenhouse gases, and that most of the increases in greenhouse gases were due to human activities, especially the burning of fossil fuels and deforestation. Findings were also that the human-induced changes to greenhouse gases are changing the Earth's climate. And if greenhouse gas concentrations continue to rise, the Earth is likely to experience rapid atmospheric warming and climate disruption during this century. And Earth's global average surface temperature in 2020 tied with 2016 as the warmest year on record. And that is according to NASA. And 2019 is the second warmest year on record, just behind 2016. But that statistic came out in 2019 before 2020 tied with 2016. The Earth's average global surface temperature rose 1.7 degrees Fahrenheit between 1906 and 2016, and 10 of the warmest years on record have been since 2005. And then a national climate assessment in 2014 shows that there was 97% scientific agreement that climate change is happening now and it is caused by human activities. And this shows the global average temperature in 2022 is estimated to be about 1.15 degrees Celsius above the 1850 to 1900 average. So that's why these numbers on the left are not in temperatures, they are in anomaly compared to the average temperature of 1850 to 1900. So you get the average between 1850 and 1900, and you use that as the baseline, and that would be the 0, and then you see if temperatures are below or above the average. And we can see a distinct rise in temperatures where you have a steeper slope of the graph, where it increases steeper. And we see 2015 to 2022 are likely to be the 8 warmest years on record. And again, starting around here, this is where we really see this steady increase. And it is projected to just keep going the way it is going right now. Keep going up. That's called extrapolate, where you look at the slope of the graph or the curve of the graph, and you extend it, assuming that the pattern might be the same into the future, and then that would tell you the increase in temperature above the average between 1850 and 1900. That would be about 1.4 around here. And this report just came out, and it's the state of the global climate in 2022. And you can look at the information at this link, and it states that in the period from 2013 to 2022, the global average temperature was an estimated 1.14 degrees Celsius above the 1850 to 1900 levels. And this is a report that's done by the UN agency's Provisional State of the Global Climate in 2022. And according to that agency, the warming continues, accompanied by accelerating sea level rise, record-breaking glacier melting in Europe, and extreme weather. And here is a website related to this report where you can click on the different areas of the world and it gives you some information. So let me go show you that. So I'm here at this website and there's a whole lot of information, and then you scroll down and there's information about greenhouse gases. So definitely take a look at this website. Okay, and then I scroll down to the bottom of this rectangle in the middle, and we get to explore the state of the climate by region. So you can click on different areas. Here's Europe. And then it opens up the state of the climate in Europe. And you could read all this information. Then we can click on Africa, the state of the climate in Africa in 2021. So you can take a look at this information. And while you're on this website, at the bottom, you have the IPCC. And there's a lot more information here on the different reports. So definitely take some time to explore these sources. Now we're back to the lecture slides. And there's just a quick video that I want to show you. What are the likely effects of climate change? As ocean water warms, it expands, which leads to sea levels rising. And much of the sea level rise is attributed to the ocean water warming and expanding. And then you add to that melting of polar glacial ice and sea ice, which also increases the volume of ocean water. And that could lead to significant flooding of coastal areas. We're also going to continue seeing shifts in locations where certain plants and animals can thrive. So that would shift our agricultural patterns. More extreme weather is expected, for example, stronger hurricanes with more rain due to increased evaporation and warmer seawater, and those are both factors that feed hurricanes. And we saw this with Hurricane Harvey, Hurricane Maria, Hurricane Dorian. Those are examples, and we're probably going to continue seeing very large hurricanes. Heat waves, forest fires, bushfires, and droughts. For example, we saw a major bushfire or major bushfires in Australia in 2019 to 2020, and July 2019, we experienced very hot temperatures locally where it felt about 115 degrees in some areas of New York and New Jersey. Not sure if you remember that, but that particular day, it felt like 115 degrees, which is unusual for the local area. We're also going to continue to see famine and desertification, and overall, just a lot of dire, serious effects of climate change. What are some strategies for preventing and reducing greenhouse gas emissions? We can improve energy efficiency to reduce fossil fuel use, especially the use of coal. Shift from non-renewable fossil fuels to a mix of renewable energy resources like wind, solar power, hydropower. Stop deforestation. And a lot of that has to do with us needing the trees and other plants in forests that help absorb carbon dioxide from the atmosphere as part of photosynthesis. And we could shift to more sustainable and climate-friendly agriculture. For example, eating less beef because cows release a lot of methane into the atmosphere, which is a very strong greenhouse gas. Also, manure from all livestock animals releases methane as well when it is stored in waste lagoons at feedlots. Governments can help reduce the threat of climate disruption. So in 2015, there was a Paris Agreement, sometimes also called the Paris Accord. The Paris Agreement's central aim is to strengthen the global response to the threat of climate change by keeping a global temperature rise this century well below 2 degrees Celsius above pre-industrial levels, and to pursue efforts to limit the temperature increase even further to 1.5 degrees Celsius. So what this means is we look at pre-industrial levels and we want to try and keep the temperature rise below an increase of 2 degrees when you compare it to the pre-industrial levels. The agreement is also aiming to strengthen the ability of countries to deal with impacts of climate change. So we have financial flows, new technology framework, an enhanced capacity building framework. And this will all support action by developing countries and the most vulnerable countries. And the agreement also provides for enhanced transparency of action and support through a more robust transparency framework. And you can look at more information about the Paris Agreement here. So here's the website, and there's a section on the Paris Agreement. So you could read through that. Then also there is a movie called An Inconvenient Truth, and that was a movie with Al Gore. And then there was a sequel, which is called An Inconvenient Sequel. And the sequel deals mostly with the Paris Agreement. And the first movie deals a lot with presenting the information about fossil fuels and greenhouse gases and increasing temperatures and what all the projected effects are going to be about climate change. So here is a link to that. I just want to show you, it is a 2006 movie. So at this point, it's pretty outdated, and that is why there is a sequel. But it is a very good movie, and if you're going to watch the sequel, you probably should watch An Inconvenient Truth first. And then there was another movie called Breaking Boundaries, The Science of Our Planet. And that's a recent movie, and that is also very informative and very interesting. And that brings us to the end of the lecture on the atmosphere and air pollution. Thank you for watching.